Okay, go ahead, Pat.
All right. Good afternoon, and we'd like to welcome everyone to our webinar, Dual Integrated Appliances as an Energy and Safety Solution for Low-Income Weatherization. I'm Pat Hellman, the Principal Investigator and Lead for the NorthernSTAR Building America Partnership that you'll hear about in a little bit. And it's our pleasure to coordinate and host this event today.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to our webinar, Dual Integrated Appliances as an Energy and Safety Solution for Low-Income Weatherization. I'm Pat Hellman with the University of Minnesota and the lead for the NorthernSTAR Building America Partnership. It's our pleasure today to coordinate and host this webinar for all of you. You'll hear more about Building America and NorthernSTAR in just a few minutes. Basically, this afternoon's webinar is scheduled for 2 hours. We'll have a short introduction, including a piece on Building America by Chuck Booten from NREL, myself, in terms of introducing you to our team. Then there'll basically be two sessions. The first session will really be focused on a particular project around dual integrated appliances focused at a weatherization application by some of our partners from the Sustainable Resources Center and Center for Energy Environment. Following that first section, we'll have opportunity for some questions and answers, and then we'll have a second part that will be coming from our partners and colleagues in Building America, the Building Science Corporation team and the Gas Technology Institute or PAR team. So that's kind of where we're headed today. A couple of just kind of background things for the webinar. As attendees, you should be able to see a screen that would allow you to have a chat box that you can use that, and the question box to basically send us questions during the course of the webinar. If that appears to be too small, you may have to click on the little plus sign on the top left corner of that chat box to open it up far enough to see it. So, and the same goes for the question box. Again, go ahead and type in your questions. You will be in listen mode only. Type in your questions. We'll be tracking those and handing those off to the presenters, as I mentioned earlier, at the end of both section 1 and 2. All right. With that, I'd like to introduce Chuck Booten. Chuck is a senior engineer and research coordinator for Building America at the National Renewable Energy Laboratory. In that capacity, he monitors the research activities for several of the Building America teams, including our NorthernSTAR team. It's one of those. He assists in coordinating the Building America activities with other DOE, Department of Energy programs and initiatives, and his research background and interest is in software accuracy and experimental heat transfer. And with that, I'll turn it over to Chuck. Chuck? Yeah, you have your mute on, I believe. I apologize, folks. It looks like we may have a small glitch here. We'll try to bring Chuck up on to give us a short presentation on Building America in just a second.
Hey, Chuck, little green microphone next to your name.
Hello, can everybody hear me now?
Yeah, there we go. We got Chuck.
Okay, sorry about that. Sorry, I don't know how that happened, but sorry about that. So good afternoon, everybody, and I'm going to give a brief presentation on an overview on Building America for those of you who don't know. Building America is a Department of Energy program whose purpose is to accelerate the development and production scale implementation of reliable and effective whole house packages of energy efficiency measures in new and existing homes. And the real key here is cost-effective energy savings. There are a lot of ways that you can save energy, but doing it in the most cost-effective way is a lot more challenging. The energy efficiency solutions in Building America are tailored for each major U.S. climate region such that they can be implemented on a broad basis while also reducing risks, increasing durability, and providing a reasonable return on investment to homeowners. These improvements are accomplished through 5 major areas. That's multi-scale research, that's laboratory through field testing, systems development, systems integration, large-scale field implementation and evaluation, and then also effective communication of these results to interested stakeholders. And to help accomplish this, DOE and NREL partner with teams of industry experts, which we have listed here, and these are our Building America teams. These teams are really the boots on the ground that help provide the highest quality research and also have the industry knowledge and the experience to implement this research in the real world. That's a brief introduction, and Pat, I'll turn it back to you.
All right. Thanks, Chuck. I want to do a quick recap or introduction overview, if you will, for the NorthernSTAR team, and just give you a little flavor of who we are and what we do. Our goal is to explore the next generation of high-performance homes for cold climates using building science as our compass and research as our guide. One of the things that has been unique for our team, but maybe not unique, but certainly a critical part of our team and our approach to the Building America Challenge is to think of not just the house as a system, which is a common approach to thinking about how houses work as an engineered system, if you will, but also paying attention to the construction or delivery system and all of that within the context, of course, of the market and user system. Today we're going to be looking at a particular technology, a dual integrated appliance, also called combis or integrated space and water heating systems. It's a particular technology that fits nicely within the house system circle, if you will. But we're going to be talking a bit about how to apply that, take it into the marketplace. Could be the weatherization marketplace will be our focus today, but also how does that get adopted by the private sector marketplace? How does it get used by the end user? But also how does it get delivered, and what do contractors need to know? What things do we need to make sure are being attended to on the construction delivery side as well? So that's just one example of kind of following through with the three system approach. Our research, as Chuck mentioned, we're looking for whole house and systems engineered solutions that will provide us the least cost and highest value for the end user, the customer, the homeowner. We're looking at, in our case, solutions targeted towards cold climates. We have a number of strength areas in our team, including the building enclosure, high efficiency mechanical systems, and we have a strong background and base in moisture and building durability and healthy indoor air as well. This team is led by the University of Minnesota. I'm Pat Hellman again with the Cold Climate Housing Program, serve as the one of the leads, and I have a partner, John Carmody, Center for Sustainable Building Research, who is assisting us with our Building America work here at the University of Minnesota. We also have outside partners, including the Center for Energy and Environment. You'll be hearing from one of their folks here in a little bit on this project, Building Knowledge, Inc., and 2 partners in Wisconsin, the Energy Center of Wisconsin and the Wisconsin Energy Conservation Corporation. We have a number of research partners that we work with as well that help guide us and keep us connected to the field, if you will, and the work that's going on out there. And I also want to acknowledge our industry partners. Each Building America team has a number of industry partners that once again connect us to the real work in the real world, and we thank them for their support. They give us important guidance on our projects as well as frequently financial support to carry out and conduct our work. You'll see in this particular case in our mechanical systems, A.O. Smith has been a strong partner in the project that you're going to hear about today, along with a number of other manufacturers that I'm sure will be mentioned later. Our portfolio this year for 2011 consists of a number of key projects around high-performance new homes, assessing what's working and demonstrating for builders what's working, looking at window selection criteria and guidance for new homes. We have a project looking at energy audits and assessing their effectiveness, both in terms of house characterization data and how that gets collected, as well as what types of energy audit tools are used, and comparing those tools to see which ones would give us the best insight into how that building's working and what we might be needing to do to improve its performance as we implement energy conservation measures under the Building America banner. Our team has a strong presence in foundation insulation systems and actually have 3 projects this year, and that one focused on new construction, much higher R-value requirements for new construction in our new codes, how we want to accomplish that, and 2 projects in retrofit, one looking at interior applications and some of the challenges and issues with that, along with a kind of a novel approach to trying to insulate the exterior of existing foundation systems. Another project is Project Overcoat. Actually, you see a picture of a prior demonstration house using the overcoat system in new construction, where basically we're putting an exterior moisture management and thermal insulation system over the entire building to achieve high levels of continuity, high levels of air tightness, high levels of energy performance. And we believe this technique can be used for existing houses as well. But what we're really here today to talk about is the integrated space, water, and heating systems project that we working with our partners, Center for Energy and Environment and Sustainable Resources Center, and where they're basically doing both laboratory testing and set up for an in-home, in-situ monitoring project under the Weatherization banner. So with that, I'd like to introduce our first section. We have 3 speakers. I'll introduce all of them at this time, and then they'll in turn take over the mic and present the project for you. Rebecca Olson is the Weatherization Assistance Program Director at the Sustainable Resources Center. And she's worked on that for 6 years as an auditor and now the Weatherization Director. Since 1977, SRC has weatherized more than 12,000 Minnesota homes. Rebecca is BPI certified and is also a BPI trainer and proctor and president of our Minnesota Building Performance Association. Jake McAlpine, also with the Sustainable Resources Center, got his degree from the University of Minnesota in bio-based products and residential building science. He's worked for 3 years at SRC as an energy auditor in the low-income weatherization program, and now is project manager for the CERC grant project that you're going to hear about in just a few moments. Ben Schoenbauer is a research engineer at the Center for Energy and Environment. I've been working on a variety of projects in residential commercial energy efficiency there for the past 3 years, and has a master's degree in mechanical engineering from the University of Minnesota. With that, I'm going to turn it over to the team, and I believe Becky will start.
Hi, thanks, Pat. As Pat said, my name is Rebecca Olson. I am the Weatherization Director at the Sustainable Resources Center. Sustainable Resources Center is one of 31 weatherization service providers in the state of Minnesota. We constitute about 7% of the state's weatherization funds. Just a brief overview of the weatherization program. It is for low-income residents. It's for anybody who is on energy assistance currently, and it's designed to save energy in those homes that are being that their energy bills are being subsidized by the taxpayer. So we are restricted by a few rules. The energy retrofits must pay for themselves over their lifetime. We have about a $6,500 average that was increased recently with the stimulus package, and that's just an average. So they range, from a few $100s to several $1,000s. The program consists of an energy audit as well as work order specifications, mechanical retrofits oftentimes, and most of the time air sealing and insulation work. Go ahead. We are able to seal homes tighter and tighter these days. We have kind of gone away from the building tightness limit era and are focused on doing as many energy efficiency measures in homes that we can. So what that has led to over the years are some combustion safety issues, as well as some moisture issues. So we are able to use some of those funds for health and safety that's related to the energy work that we do. So that budget is about $1,000 average per home. It's not a limit, it's an average, so again, we're able to spread that out, but it is somewhat restrictive. So many of the homes that we have done in the past couple of years have needed mechanical replacements on their furnace or boiler for energy efficiency. And so what has happened is we have orphaned quite a few water heaters, or they have been orphaned as we come in to do the energy audit. Those then require us to address through our health and safety budget, since we're not able to have a cost effectiveness measure for the fuel combustion high efficiency water heaters, since the cost is not, or the upfront price is a little too high. So we're putting in a bunch of 60%, right here it says direct vent tanks or power vented water heaters. It was hard for us to feel comfortable with replacing a bunch of expensive mechanical equipment with just a very small energy savings. So we started to brainstorm and figure out how can we, since we're replacing all of these water heaters anyway, is there a way that we can actually cost effectively improve the energy of these units? So we started in our hydronic heated applications, integrating the water heaters with our boilers, which is pretty straightforward and has been done a lot. And we made it work with our rules through the weatherization program. However, probably 90% or so of our housing stock has forced air delivered heat. Our area is one of the suburban sections around Minneapolis, so most of our heat is forced air. So in the past couple of years, we have replaced about 47% of the forced air water heaters, or sorry, forced air furnaces, and about 48% of the natural drafting water heaters. So this became quite a big concern for us. So we started to do some research on integrating these systems for forced air, and found that there were several products out there. The price point seemed pretty high to us compared to what we thought they could come down to. So we were trying to look at ways that we could start integrating this into the program. And right about that time, the Sustainable Energy Resources for Consumers grant came out. And it was a grant that was basically made high-performing weatherization agencies eligible. And Sustainable Resources Center was one of the agencies across the country that was eligible for this. So we thought this was a perfect fit. So we submitted this application. We thought we could work on about 400 homes in the state of Minnesota, which is what we are currently working with. And we are partnering with 3 other weatherization service providers, one in Minneapolis, and then 2 in outstate areas. So most of the 400 will be done in the Minneapolis area, but that is kind of our scope of work, and I'll turn it over to Jake to talk about the systems.
Hi, Jake McAlpine, Sustainable Resources Center. So just some kind of general definitions. Dual integrated appliance is a mechanical system that combines both the space heating and the hot water heating into just one appliance. For our purposes, we'll be dealing with natural gas as the heating source. We can do this in a couple different ways, as Becky mentioned. In a hydronic setting, we can do this by a sidearm water tank to provide the domestic hot water, while the heat is provided through a radiator or in-floor system. And then in the forced air application, we can do the domestic hot water through a boiler or a water heating system, and then integrate with the existing ductwork with a hydronic air handler. These systems can be both closed loop or open loop. And open loop systems can use the water for either or both the space heating or the domestic hot water, while a closed loop system will have those segregated, and there'll be specific water that will do heating and a separate water that will be used for the domestic hot water. This is just a general diagram of how an open loop system works. You can see the tank here on the left. This would be accurate. This is entirely open within here and can either be pulled by a domestic hot water load or the pump on the hydronic air handler, which can be engaged by a thermostat, could pull water in that direction. And then the water will run through the hydronic air handler and then is returned back to that storage tank. All of the components within the hydronic air handler that come in contact with the water are potable rated, and there's a pump that is built within many different models that will periodically pulse to move water through that hydronic air handler to prevent stagnation. So the water can be used for heating at one point and then at a later time be drawn out through the domestic hot water line. This is a diagram of a closed loop system. There's a lot of variability between the different units that we've looked at, but this is just a general layout. You'll see on the left here that there is a separation between the domestic and the central heating loop. So you will have a heat exchanger, and usually a three-way valve. It depends on the system. The water will be heated and either will run through a space heating loop and then can go out to the primary and then secondary loop and into the air handler, or usually there's a three-way valve that will send it through a brazed plate heat exchanger, which will then heat the water, or in this application on the right here, it is actually an indirect loop that heats the storage tank. Primary and secondary loop, this will just have a pump on the inside of the boiler unit, which will circulate water, and then a separate pump, again, that's connected to the thermostat, usually to engage the secondary loop and pull the water into the air handler. So why did we decide to look at dual integrated appliances? As Becky mentioned, we were working under a number of constraints, and we're replacing a lot of units already. We like the idea of being able to get both our space and our water heat done with high efficiency units. There are definitely cases where if you are already going to be replacing a furnace with a 2 or 3 stage natural gas condensing furnace and a water heater, there's times that these types of systems can be cheaper. There's certain circumstances as well where they are definitely simpler and there's less maintenance involved in them. A great example of that is the air handlers themselves. Replacing a furnace with an air handler, you can have a lot more maintenance involved in maintaining the furnace, whereas the air handler is, on its basic level, a fan, a pump, a coil, and then some controls. You need to keep the coil clean and keep the fan clean, and besides that, maintenance is quite limited on them. We did like the sealed combustion aspect as well. That is a big concern for us in weatherization, is making sure that not only our houses are energy efficient and durable, but that they're also safe for those homeowners. So that's something that we tend to jump over a lot, but it's a big driver behind this as well. And then we like the fact, too, that if we know we've got sealed combustion for both our central heat and for our domestic hot water needs, that really does open us up to be able to do more air sealing if the house is set up in a way that it doesn't need combustion air anymore. We can seal that. And then we also, depending on where the venting is going, have the option of doing a lot better job sealing around the chimney. So once we kind of decided that this is a feasible route and wanted to pursue it, we ran into some issues up front with the contractor's level of experience with these units. So we would get bids, and we'd see a price that we thought was pretty high, and there was a lot of contractors working in the uncertainty that they had about the system. They weren't familiar with them, and that was reflected in the price. With the wide range of products that we found, there was a lot of contractors who didn't have personal experience with those, so then we started relying, or they would rely more on product reps to get information. And although product reps are a great initial source of information, just by their nature, are fairly biased as to how their products perform compared to others. So we weren't really sure that we were getting what we wanted when we would just talk to them. The schematics for wiring, especially with kind of getting the thermostat and the heating plant and the air handler to talk to each other properly, often that had to be worked out on site, which really did increase cost a lot. We've since then been able to work directly with the product manufacturers to get specialized schematics that would clarify how they want them set up when we're using these applications. Another really big thing we ran into was sizing. When contractors are looking at replacing a water heater with another water heater, they can go off the existing size. Oftentimes the people in the house have modified their behavior to fit with the piece of equipment. But when we're really changing how that piece of equipment works and integrating central heat into there and having a much larger burner in there, the sizing became an issue. There was a lot of kind of guessing that was going on, and we really wanted to make sure that we got that nailed down properly. All the components were coming. There's a couple manufacturers who would make systems that would have both the air handler and the heating plant, but we were finding a lot that weren't matched up that we wanted to work with. So that led to some compatibility issues. And then basically one of the largest ones is that when we would set these up according to the manufacturer's specs, we definitely were not putting our heating plants in a situation where they would be able to condense. So our performance was dropping, and being able to flush that out and figure that out was also a big need that we had. So we partnered up with Building America Group here and Center for Energy and Environment, and with them we're able to set up a lab and get about 9 different heating plants and probably close to a dozen air handlers now into that lab, get them set up where we could start to work through some of these problems that we've seen, and then use that information to help the contractors understand the units, give us information about how they perform, and kind of give us the best chance of being successful with that. So here's just a couple shots of the lab. You'll see in the upper right there, we have got the 9 heating plants, all of the vertical venting going out the roof, and some of the air handlers next to them. We used flexible PEX line to be able to move the air handlers around to different heating plants and be able to connect them and try them in various different combinations. So with that, I will hand this off to Ben.
Hi everyone, Ben Chambar with the Center for Energy and Environment, and as Jake and Becky kind of mentioned as they're getting into this project, they smartly had budgeted part of the project to do some research and do some analysis of the systems to look at things, and they came to us in Building America, and we developed this lab idea to really look at things and get things set up going good from the beginning. So we developed a few different tests to do on the heating plants and the air handlers, just to look at them and see which ones we wanted to use and which ones worked well together. We started with doing an idle test just to see how these systems performed when there was no heating load or water heating load. And then we looked at the steady state efficiency for space heating. Then we looked at how the air handlers performed at different set parameters and over different ranges, and sometimes looked at the manufacturer spec ranges, but also looked sort of above and below those ranges to really see what the best performance was for those air handlers. And then we put the air handlers and the heating plants together and did some full system tests that were running different usage profiles and loads on the systems to test their cyclical performance, their maximum capacity, and some some outlet temperature performance. So we'll start with the idle performance, the idle standby testing. This chart shows the gas usage and electric usage of the different heating plants when they are just sitting in idle with no load applied. So we here I have it presented in dollars per year using $1 per therm and 12 cents per kilowatt hour. So you can see that we have on the left we have the boilers. Then in the middle we have the tankless units, and then on the far side we have the tank type units. So the first thing that jumps out is this really big boiler. That's a boiler with a combi boiler with a with a domestic water tank inside. It's about a 12-gallon tank. Then the two boilers with no gas usage are the no-mass boilers that have no storage capacity, so they don't use any natural gas. And then the other boiler is a 6-gallon internal domestic water tank. The two tankless water heaters, the one with no gas usage, the tankless water heater 1, is a traditional tankless. The other tankless water heater has a 2-gallon storage tank. It's more of a hybrid storage tankless water heater. And then the three tanks, tank 3 has a 34-gallon tank, and the other two tanks are 50 gallons. So you really can see how well or not well in some cases the heaters are insulated. For instance, boiler 1 that only has a 12-gallon tank, uses about $100 per year, whereas the 50-gallon tanks are using less than $50 per year. So it was really pretty interesting to see. So we continued looking at that by taking some IR pictures of the different units as they were in idle. So this is first the boiler with the big idle losses with the 12-gallon tank. And you can see actually the tank is on the right side of the unit there. It's actually not that poorly insulated. The tank actually has pretty low heat losses, but what's really losing a lot of heat is those exposed pipes and heat exchanger on the left side of the unit. They're really radiating a lot of heat off, and that's just with it sitting in idle. So here's a traditional tankless water heater with no storage capacity. Using the same temperature scale, you can see that there's very low heat loss here. Really, the only part that's losing any heat at all is the electronic controller, which makes sense because it's just using a little bit of watt to keep that power, a little bit of watt power to keep that controls going. Oops. And then the last IR picture we have is of the hybrid tankless with storage, and you can see there that the tank is we're losing a little bit of heat off the top of the tank and a little bit off some of the piping inside, but for the most part, it's pretty good. Although, when you think about it, it has about the same heat loss rates as the 50-gallon tanks, and it's only a 2-gallon tank. So there's some room for improvement there as well. When we were looking at this unit, we did notice that the insulation that they use is pretty loosely fit to the tank, and there's not a lot of it. And through discussions with the manufacturer, it sounds like they're looking into this, and they're really interested in learning why the heat loss is bad and trying to improve it in standby mode. So the next type of test is a steady state simulated heating load test. So we approached this. We used one of the heating plants. We ended up using the tankless water heater that provided the most consistent water temperature. And we plumbed that into the return of the different heating plants to simulate the return water coming from a coil or from a hydronic air handler. And we varied that temperature and flow rate so that we could see how the boilers and the water heaters would perform under different return water conditions. So simulating working with different air handlers and different heating loads. So this plot is kind of complex, but it shows the efficiency on the heating plant, steady state efficiency on the y-axis, and the different return temperatures at the x-axis. And this plot shows for 4 gallons per minute, and the chart would vary some for different flow rates. But what you can really see here is how, as that return water temperature increases, the efficiencies really drop off. And this is important because a lot of the air handlers were set having high flow rates and high supply water temperatures on the heating units, which would guarantee, which pretty much, in most cases, gives you pretty high return water temperatures and therefore low space heating efficiencies. So as we learn more, we really wanted to shoot for where the kind of knee in the curve is, and the efficiency really starts to drop off for a lot of the units around 110 degree return water temperature. So that sort of set our goal for air handler performance. Also, it's important to note here, it says in the bottom here, with about a 10% decrease in efficiency, you're going to increase your heating bills by about $150 a year. And when you look at over the lifetime of the heating, the heating system, that's a pretty significant amount of money. So it really matters to get these things set up right, and there's some significant savings involved. So the next test we looked at was to test just the air handlers and see what capacities they had and how operating them at different controls affected their performance. So we measured the flow rate and water temperatures into and out of the air handlers, and then the air flow rates and air temperatures. We were also curious about, on the air temperature side, just making sure that we had a temperature that would be acceptable to the homeowners. One of the constraints we have with this project is that we don't have money to affect and change the duct system, so we sort of have to deal with what we have. And in some cases, that may not be set up the best, and we might have ducts that blow on occupied areas or blow on people. So we want to make sure we're not setting ourselves up for a situation in which people are going to complain about cold water. So we did some air handler performance mapping, and this kind of goes with the sizing aspect that Jake was talking about. We set a minimum supply air temperature that we wanted of around 110 degrees, and that kind of dictates the one side of the flow rate bound, and then we set a maximum return water temperature that we wanted, and that really gives us our flow rate range, and that flow rate range shows us what the coil capacity is. So here's an example. If we look at, for one air handler, if we look at the supply chart on the lower left-hand side there, we can see the red for a lower CFM rate and the blue line for a higher CFM rate. If we set our minimum air temperature at 110 degrees, that gives us flow rates that have to be greater than 2.2 and 2.6. And then a similar thing can be done with the return water temperature. That gives us the high-end flow rate. And then using those flow rates in the CFM supplied, we can see the heating load that air handler can reach. So this air handler we have a range of about 45,000 BTU per hour to about 57. We also took information about the electrical consumption of the different heating plants, just to see how that played in. So here's 4 different heating plants and how their watt consumption changes with the CFM. All these, when picking the units, we were concerned with the fan power usage, so they're all ECM motors already, so the watt draw isn't real high. It is about $15 per year increase for every 100 watts you increase on the fan power. So I guess that's a lot smaller than the return water temperature effect, but it's something to think about as well. So then we moved on to the full system test. We ran these 3 different profiles with each heating plant. So the blue sort of represents the domestic water usage, and the red represents the space heating load. So with the max capacity test, we really wanted to test to see what the performance was under a high use load. So you can see there we kind of have a shower turns on, then a second shower turns on, then the first shower turns off, and the second shower turns off. And during that whole time, we have a space heating load. The DHW interrupt profile is really looking at what happens when there's a shower on and the furnace kicks on. Does that interrupt service? Does it not perform well? Those different things. And then the third profile, the low use profile, is really just looking at the ability of the system to provide water, domestic water needs at some lower flow rates and for shorter time periods. So that's the first thing we'll look at here is the low use performance. So this is a plot that just shows the water temperature as we progress into the draw. So that somebody turns on the faucet at 1.2 GPMs, at time 0. And then on the y-axis there we have the temperature difference between what is actually coming out of the water heater and what the set point is. So for the tanks, which are shown in this plot here, we have a set point of 120 degrees, and you can see pretty quickly they get up to 120 degrees and are pretty consistent. So we have 120 degrees coming out within about 4 seconds of when water is initially drawn. If we add the tankless water heaters to that plot, you can see it takes them an extra 35 seconds to get up to temperature in the one case, and an extra 20 seconds or so to get up for temperature in the other case. And these temperatures are taken right at the outlet of the water heater, so that's just the time it takes for the heat exchanger to heat up inside the unit. And then if we add the boiler, we can see there's some different performance going on here. The two on the lower side that look a little bit like the tankless are those no-mass boilers, which have a very similar process to creating hot water. They need to heat up that heat exchanger and get to create the hot water. The two that are on the higher side are the boilers with the dashed lines there, are the boilers that have the internal tanks. And in both cases, the internal tank is stored at a higher set point than what we're asking for domestic water. So in the one case, it initially puts out a little bit hotter water and then comes down to around the 120. And in the other case, it never comes down, which is a concern. And yeah, so it's definitely a concern with the systems. I should say with all these systems, we are using a mixing valve down the line. And so that would alleviate some of the concerns with this high temperature. The things that it doesn't alleviate is that high temperature is part of the reason that there's an increased standby loss in that boiler, and eventually it will come down to the 120 set point, and so that might provide some problems if you set your mixing valve to handle that peak, and then eventually it does drop down to the temperature it's supposed to. So the next thing we'll look at is that DHW interrupt profile, again shown up in the upper right-hand corner. If you're interested, the dashed line there is the point in which the space heating load kicks on. So before that, we're seeing just the steady outlet temperatures for the different heating plants, the tankless in green, the tank in blue, and one of the boilers in red. And you can see that the tank capacity of the storage and of the boiler help even out that transient performance, that change in performance. Whereas with the tankless, it needs a little bit of time to adjust to that increased load, and so you see about a 4-degree dip in temperature. And again, these temperatures are taken right at the outlet of the water heater. If we did look at this curve down the line after the mixing valve, some of that dip would be reduced due to the mixing at the mixing valve, so you are alleviating some of those effects there. And then the next test we looked at was the max capacity test, and so this is really where we wanted to look and see how large loads affect each of the heating plants. And so we had about a 40,000 BTU per hour heating load going the entire test profile. We had about a 12-minute 70,000 BTU per hour shower, and then a secondary shower that was about 10 minutes long at about 55,000 BTU per hour. And so, these I guess aren't the worst case showers. They could potentially be a little worse in the dead of the winter. You might see somewhere up to 90,000 BTU per hour. So this chart shows sort of the change in outlet temperatures on the y-axis. So we're looking at the difference in temperature at the beginning of this profile, so right after the first shower comes on, to the final temperature, shower temperature at the end, or the temperature being output right when we turn off the shower. So if you see a significant drop in the temperature, that means that the heater is struggling to keep up with that load. So you can see with the tanks, especially on the DHW side, we're losing 20 degrees on the first, 10 on the second, and over 20 degrees on the second. And that's just because that capacity of the tank isn't able to match. So the burner input is about 100,000 BTUs, and the tank is starting to run out of heat. With the tankless water heaters, you see that they're keeping up fairly well. They actually increase both the domestic and the heating supply temperature over the course of the 15-minute test period. And then with the boilers, all the boilers have domestic water priority. So you can see that the heating supply side, there's a big temperature change, and that's just because it's no longer supplying heat to that side. You can see the middle two boilers do a good job. They actually keep the DHW temperature constant like you would expect. The first boiler only has a 75,000 BTU per hour input. So that's why you see about the 10-degree drop, is that it just can't keep up with the 2-shower load. And the fourth boiler is that boiler that had that high increased temperature. So as the temperature started to come down to the set point, we saw big DHW drops. And actually, in that case, the boiler couldn't extract enough heat from its internal loop and put it into the DHW tank that it actually dropped below the set point. So you see an over a 60-degree temp drop for that high use case. So we'll talk a little bit about sizing. As Jake mentioned, this was a big issue when we started to try to look at the systems. We could find little or no sizing information from the manufacturers. They typically allow the manufacturers' reps or the installers to do the sizing, and a lot of times they don't provide strong reference material to those people, and so it becomes kind of a in-the-field sizing that maybe isn't consistent site to site. So we developed our own sizing guide to really try to make sure we were doing a good job of getting these installed in an application where they'll work well. And it was important to take the lab testing into consideration when we did the sizing, so that we could make sure to install the heating plant in a situation in which they would likely condense and perform at a high efficiency. So we based our sizing guide on both the input rate and the storage capacity of the heating plant, and then we compared that to the household load, so the number of showers on the DHW side, because that's really the big load that worries us for sizing, and then the estimated heating load on the design day. So for example, we found that a storage water heater with 130,000 BTU per hour input in a 50-gallon tank would sort of max out at a 60,000 BTU per hour house with one shower. So talk a little bit about the field project that we're just sort of, we're really starting to ramp up the installs. So Becky mentioned that we have 400 installs. Those all need to be in by March. And we've gotten sort of the preliminary installs in, and we're really starting to ramp up to try to reach that number. All 400 houses will undergo a utility billing analysis on the pre and post data. And then on 20 selected sites, we're going to do an additional detailed monitoring, and that's going to include both pre and post monitoring. We'll look at starting the pre-monitoring in the next month or so here, and going for about a month and a half, just measuring the energy consumption of the existing equipment. And then we'll switch to doing some monitoring on the newly installed dual integrated appliance for the rest of the heating season. And that monitoring will give us information about energy consumption, but also about system efficiencies. And it'll be pretty detailed data, so we can really see how these things are performing and if we got the parameters and installed conditions that we were hoping to achieve. So just want to talk a little bit about the system costs, because that's pretty interesting for the first kind of 12 or so installs that we've done and a couple of bids. So we used a few different contractors, and right now the first systems were just installed with one of the tankless water heaters and a couple of the tanks, and those selections were mostly due to the water hardness levels of the sites that we were installing at initially, and they were a little bit higher, so we had to have systems that could handle the high water hardness. So here's a breakdown of install costs for two contractors. So in the blue we have the labor cost, and the green is the equipment cost. That's just the water heat or the heating plant and the air handler, and then the red is permits, sort of miscellaneous parts, and some other miscellaneous costs. And we have a few different systems. You can see in the bottom there the different heating plants that were used. You can really see that the first thing that jumps out is that the big difference between the two contractors, see it's about $1,000 or $2 less per install between the contractors. And that you can also see there is mostly due to the labor costs. Contractor B has a $1,000, maybe more average install or average labor cost, and also an increased miscellaneous cost. The equipment costs are pretty, it's kind of hard to see on this graph, but are pretty consistent across the different contractors. But the labor costs are considerably different. The other thing that's interesting is that despite the fact that the labor cost is a little higher, the overall cost for the tanks water heaters based systems is cheaper, and that's just due to the cheaper cost of the tankless water heater than the storage water heaters. The other thing, so that's the first thing we're interested in price is the different system costs and the different costs from different contractors. The other things is kind of how things change over time. And so this chart just shows 6 installs from contractor A. The black bars show the kind of first bidding or the first jobs that they did, and the gray bars show the second round. And you can see that for each heating plant, we saw a reduce in cost in their second install than from their first install. And this was especially good when considering that contractor A was the lowest cost of the contractors that have been used so far. So if the guys that are doing the best job or the cheapest job can reduce their costs, likely that everyone can have some cost reductions. So some of the expected results from the field study, as I mentioned, is just these better understanding of installed costs for the different systems, for the different contractors, and how those things change with contractor familiarity. We also want to learn about the system design specs and quality control needs we have. So how do we tell the contractors what we want installed, and then how do we check to make sure that those systems are being installed like we want? And then just the installed efficiencies of the DIA systems, their savings potential, and some of the lessons learned from installing them, and how the homeowner feels that they did in heating the home. And with that, I will throw it back to Pat and take some questions, I believe.
I should be back, and we have an opportunity here to answer some questions. As you can see, or at least I hope you get an appreciation for what the project's about and how exciting it is. We've been really excited to work with these partners and have the opportunity to use Building America as a way to learn more about this technology and to partner up with a really exciting existing project. That's always hard to find. We were really tickled to find this project out there. And it's even more impressive when you find partners like we have that are very bright and sharp and really working on critical issues. So with that, I'd like to see if there are any questions, and we got one queued up here. Will you be doing any comparison of cost of dual integrated appliances versus conventional furnace and water heater by the same contractor? So it's kind of back to this cost question, Ben. We see how the contractors came in, but how might that have compared to a more traditional or conventional system?
Yeah, I can answer that. We are using many of our existing mechanical contractors through the weatherization program. We did do a separate RFP, but several of our existing contractors did apply for that. So we definitely will have that data on a traditional approach being a high-efficiency fuel combustion forced air furnace and a power-vented water heater. And then based on some of CEE's data for their tankless water heater study, we'll be able to extrapolate some of those cost comparisons.
Excellent. Another question. How do they plan on comparing them to existing forced air furnaces for energy performance?
So in the 20 field monitoring sites, we'll do some pre-monitoring on the existing system. So that'll just be whatever those sites have. We will be selecting the sites, so we'll have some ability to control what the existing equipment is. But on those sites, we will monitor the gas and electrical consumption versus the outdoor air temperature, I guess corrected for the indoor air temperature, and then doing the same for the dual integrated appliance after an install at that same house. So under the same load in the same house, we will have data for its energy consumption compared to the temperature.
Yeah, very good. Because it's I think part of the underlying question here is, having the efficiency of this system versus the stated efficiency of a forced air furnace aren't exactly apples to apple comparisons, but before and after gives us a good judge of that.
Right. We won't have existing efficiencies, but we will know sort of energy usage and dollars.
Yep. All right, another question for Ben. Any field validation on the Combi system guideline to ensure that it's working properly? And I suppose it might be different between tankless and boilers because of the domestic priority is kind of how I'm interpreting that question.
Yeah, and we're going to use a variety of the systems with the 20 house field install, and so we're hoping to get some of that validation of our install guide out of those 20 houses. We'll really be paying particular attention to those houses to make sure it's matched, but also we'll have the utility billing analysis from all 400 sites, which probably won't have, we'll have a little higher error bars, but will give us a good idea of how much energy we're saving in those sites as well.
Excellent. Another question coming in here. Will we be testing any integrated systems without air handlers? I suspect that's pointed towards hydronics and natural gas, meaning there may be other fuel sources.
Under this project, we're sort of constrained to forced air and natural gas because that's the majority of the housing stock that we're working with here in Minneapolis. I guess there's potential to expand in the future, but that seems to be our focus right now.
Yeah, well, that may also be a good question. I'll try to remember for our next two presenters as well that are coming with experience from some other perspectives and backgrounds. They may be able to answer that question as well for us. Are there any other questions before we move into our kind of second group of presenters? I'm not seeing anything here. I think I've covered most of them, at least have come in so far. All right, you'll get another chance. So if as we go along, you can type in questions as we go, and certainly be thinking about questions for our next two presenters. But we also can obviously take questions for the previous group as well and handle those at the end of this next two presentations. So with that, I'd like to introduce our next group, our next session. We'll have two speakers, Armin Rudd and Ryan Kerr. I'll introduce both of them up front, and then they'll just hand off the presentation midstream from one to the other. These are our Building America partners that are in the Building America teams, both Building Science Corp. And then PAR, Partnership for Advanced Retrofit, Residential Retrofit. So again, they're kind of in the Building America family. We're really pleased to have them both here sharing their experiences related to dual integrated appliances as well. Armin Rudd is Principal Engineer for Building Science Corporation. He's been there since 1999, conducting analysis, design, inspection, research, and development of building mechanical systems, actively researching mechanical solutions for high-performance homes, and has had many years of experience with dual integrated appliances, or as we in the old days called them combis or combo systems. And Armin will be presenting a project, current project of theirs, looking at a dual integrated application. Ryan Kerr is Emerging Technologies Manager for End-Use Solutions with the Gas Technology Institute. The role there is to accelerate the commercialization and adoption of latest energy efficiency technologies for residential, commercial, and industrial end-use markets. He's the Program Manager for the Partnership for Advanced Residential Retrofit, as I mentioned, one of the 15 Building America teams. And prior to that, he worked for Consol, managing Building America activities in the Northwest for BIRA. So certainly both of these come to us with a great deal of experience in research in this area to begin with, but a lot of experience within the Building America program. So with that, I'm going to turn it over to Armin Rudd.
Armin, is your mute button on? Click on the phone next to your name.
Yeah, I did. I just clicked it twice, and it's working just fine. It doesn't show muted. I muted it.
You're good.
I'm on now?
Yep.
Okay. Sorry for that. I don't know how that happened. So thank you, Pat. And by way of introduction, for a little bit more of this topic, Building Science Corporation, as part of the Building America program, has been working with dual integrated appliance systems and combination space and domestic hot water heating systems since the early 2000s. We had hundreds of installations in Las Vegas and Albuquerque and Houston in, say, a 5-year period from 2000 to about 2005, using standard storage type hot water heaters with a little bit higher than normal input, 75,000 BTUs per hour and 50 gallons. And a first company air handler, actually, so combining different people's equipment, and controls that were actually developed by a partner of ours in Massachusetts. We had pretty good success with that. It's just that we ended up with some cases where check valves failed, and we ended up with heating and cooling going on at the same time, where you would have an air handler higher than your hot water heater, and you could have a thermosiphon flow that would pump up and back. And so that was a little disconcerting to some of the builders, even though we were able to fix that problem with better check valves. But at the same time, high-efficiency furnaces were really coming into their own. And so most of those builders went back to high-efficiency furnaces, condensing furnaces, and standard hot water heaters. We took another look at this whole area after the tankless hot water heaters really started to gain prominence. And in 2007, we installed a system that looked like one of the two that you see on the screen right now, and got some very good experience with that. After a few years, actually, NYSERDA, the New York State Energy Research and Development Authority, got a hold of the schematic that we had used, and had some contractor focus groups, and decided that this was something that they really wanted to work with in their area in what they called deep energy retrofits. These were houses that were insulated and sealed on the outside, and mechanical systems were changed, infiltration was dropped, ventilation was added. And so this particular project that we're going to focus on right now is a 2-family building in Utica, New York. Both of them have condensing Rinnai tankless hot water heaters, and as you can see, the system also includes a small storage tank, which acts as a manifold or a buffer in that system. This is another shot with the air handlers. The air handlers were ones that have an ECM motor for the fan, so the system is efficient in every way. And we've been monitoring those to see, and I'll get to that later, to see how they're actually working. This is a schematic of that system, and as you can see, it has the tankless hot water heater, but coupled to a small storage tank. In this case, it was a 12-gallon tank. In another case, it's been a 6-gallon tank. And so the difference between a standard tankless hot water heater application is that normally the mains water would go directly to the tankless hot water heater and come back. In this case, the mains water comes into the storage tank, and the tankless hot water heater only comes on if this pump senses that the tank temperature is low enough, and then it will circulate water through and retop off this tank and keep that tank maintained. The hydronic space heating loop is then a sidearm off of that tank. There's a mixing valve to make sure that we don't supply water that's higher than safe. That's basically the schematic of that system. All things worked well, except for really one area, and that is that we had a lot of problem with material plugging the inlet filter or strainer for the tankless hot water heaters. This is where that filter that you see on the right-hand side, the lower right-hand side there, would go. screws into this, and there's a flow meter up inside of that small port. And by the way, that's one of the problems with these systems. They have very high resistance to flow, something on the order of 30 feet of head at 5 GPM for this particular unit. And you can see that these waterways could be opened up significantly so that there was a lot less restriction to water flow, and that's something that I think the manufacturers will be looking at. Some units do have less water restriction. So another side note here, on the lower right-hand side, you see one of these strainers that has already fallen apart. And it's due to the hot water that's being circulated back through. I think that that particular material was probably considered for more water mains type temperature as opposed to returning hot water temperature. And so after about a 3-year stint, that's what this strainer looked like. So that's a significant maintenance issue. Essentially, strainers have to be, a new one has to be left in place so that this kind of a thing would not be a problem for replacement. It could be quickly replaced. So here's some material that we found beginning to collect and plug these filters, and the maintenance interval was sometimes on the order of weeks, and certainly on a month or 2-month schedule, which certainly would be way too much. Maybe an annual maintenance would be acceptable. This material, when it dried, turned out to be, seems like mostly calcium carbonate, which is something that is in most municipal water supplies, and that's something that essentially, the question becomes: do those filters have to be that tight? Can they pass that material, or is it really going to affect the flow meter or not? And we're finding out that probably they don't. Once the plumbing system catches whatever bits of copper might be in the system or metal, Bosch, as one example, says that the filter can probably just be removed without any problem. This is a little bit more of a problem, as you can see, with the Utica water supply. We had significant problems with debris coming through the system. We worked with the Mohawk Valley Water Authority for some time, and they kept thinking that, no, it's not our water, it's actually this tank that you have in the system. It's just collecting precipitate, and you're pulling water off the bottom, and it's throwing it through that filter and creating a major problem for you. So we decided to try something, and we took one of those systems and took the tank out. And this is a schematic of how that would look without the tank. So the mains water then comes through directly to the tankless hot water heater, goes back and can supply domestic use, or it can supply the space heating demand if this pump is on, the pump on the left. We had absolutely no change really in the amount of material that was collecting and in the interval of maintenance required for the inlet filters. So that didn't turn out to be a problem, but it ended up to be an opportunity for us to see and look at the performance difference between systems, one with the storage tank and one without. We did actually, in the process of everything, find a solution for that inlet filter problem, and that was to add a much larger strainer, a pre-strainer, which now is making that interval of maintenance in the case of the 2007 system, an annual basis. In the case of the Utica, New York systems, we haven't gone a year yet with this filter on, but it's been about 6 months without maintenance required. So this is about how much material collected on the large filter, but that much material on the small filter not being allowed to pass through, which actually may be okay if the manufacturers take a closer look at this. That much material would have plugged that filter. So here's just a whole bunch of data points that we're taking on both systems. Here's a plot that shows I'm just going to show some of the more significant findings. If you look at this chart on the y-axis, it's cycles per day. That's cycles for the tankless hot water heater. And on the x-axis, then you have different days that I selected to just show. And system 1 is the green. System 2 is the blue. System 1 is the one that has no tank. And system 2 is the one that does have the tank. And you can see there's about a 10 times factor difference in the number of cycles per day of that water heater. And that's because with the system that has the tank, when you get small flows, that tankless hot water heater does not have to fire. Generally, there's enough storage capacity there that many of those small draw demands are taken up just by the storage. Whereas with the system that does not have any storage tank at all, it's always trying to fire anytime there's more than half a GPM flowing through that unit. This is another plot that shows what kind of temperatures we have leaving the mixing valve in those systems. And this shows that system 1 with no tank has a very wide range of outlet temperature from the mixing valve, all the way from essentially the basement temperature, which is what the mains water temperature is in a lot of low flow situations, all the way up to what we would have wanted, which is somewhere close to 120 degrees. You can see that there is sort of a tightening of that band as you get to very high flows, but the data that we have shows that most of your flows are well below 1.5 GPM, and in fact, the greatest number of flows are the very small flows, even below 1 GPM, and for very short time periods, on the order of 10 seconds or less. So that heater doesn't even have a chance to fire and produce that hot water that would be expected. The system 2, this shows, again, the temperature of water leaving the mixing valve, and it's versus draw rate. So there is, again, a small tightening as you get to very high flow rates, but a much tighter band of delivered temperatures from that mixing valve to the use. This is another way of looking at the performance of the system in terms of comfort and acceptability. This is the system without a tank, and we're looking at these red values here, supply air temperature. These red values at the top are the actual supply air temperature from the hydronic air handler. And you can see that it goes anywhere from room temperature up to what we might like to see somewhere in the 110 to 115 degree range, which would be about what you could expect from a normal condensing furnace. The system with the tank then narrows that band significantly so that we have most of our supply air temperatures above the 100, 105 degree range that Ben was talking about. This is just another example. There's lots of examples of this in the data, but if you look at the red line at the very top, it's the orange line there, second from the top. It's the mixing valve temperature out again. And as you can see down here, we had off-on flow, small demands for domestic hot water for over 10 minutes, but that heater never fired and never changed the outlet temperature of the mixing valve. And this is the system 1 with no tank. Of course, that didn't happen with the system with the tank because you have that stored capacity. So the occupant in the house or in the unit with the system that has no tank, since we have found out that it had no impact on the clogging of the system, which is really the only problem we had, has asked for that tank to come back, which we're going to do after about half of this heating season goes through. And then we're going to have a much better look, because we've been adding instrumentation somewhat as we've been going along, and so we really want to get a better handle on exactly the efficiency and performance values as well. This is just sort of an externality complication slide that goes along with weatherization issues. Once you touch a house, you own some parts of it in a way. And this is just showing an example of this floor was insulated as part of the deep energy retrofit. There's 2 inches of insulation here, and there's a cover board of cement board over top of all of that, and that's just loose laid in that whole basement. And before these sewer caps were fixed, there was one of them that just had a rubber plug and not a screwed fitting, and it popped out and backed up sewer in this basement, and everything floated 8 inches high. Unfortunately, for the occupant, and unfortunately for the program then paid some $10,000 or so to replace this, and to take everything out, clean the floor, replace the insulation and the cover boards, and have a backflow preventer installed. And this is not unusual at all. A lot of old communities that you work in for weatherization have sanitary sewer and storm sewer tied together such that when the storm sewer overflows, it can back up through the sanitary sewer, and that's exactly what happened in this case. So now, for another $4,000, in addition to the 10 for Insight, this backflow preventer had to be installed. I think I have a few more slides related to other sites where we had accumulation on the filters, and water quality can be a main issue. Also relating to anode replacement. This is an aluminum anode rod replaced with a magnesium rod. The aluminum rods don't hold up as well in the hot water, long-term hot water applications. This is some scaling issues that we have dealt with. The upper fitting is one where calcium carbonate is being generated quite a bit. This is on the other side, in the copper side of the dielectric union. So all dielectric unions should have plastic sleeves in them. The Watts, this is a Watts product with just a galvanized fitting on one side. As you can see, all of these nipples going into the tank have these dielectric unions, but the galvanized side scales badly compared to the copper side, and the separation, the dielectric separation, is simply not adequate. There should be a plastic sleeve in that galvanized fitting. So we helped solve part of that problem with an electronic water conditioner. This is an example of pipes that were then being cleaned out from that scaling after weeks and even some months of using the electronic water conditioner. That's the end of my presentation. I think I'll be turning it now over to Ryan Kerr from the Gas Technology Institute.
Thank you, Armin. I'm going to talk about, kind of shift gears here and chat about the appropriateness of these technologies for energy efficiency programs. This could be whole home energy efficiency programs, single measure energy efficiency programs as delivered by a gas utility, or possibly weatherization. As introduced, I am Ryan Kerr. I work here at the Gas Technology Institute and also work with the principal investigator, Larry Brand, on the PAR program. So super quick overview of who we are. We're the research arm of the natural gas industry, a nonprofit with 65-year history. We're based outside of O'Hare Airport in Chicago. We have 28 specialized labs, including the residential and commercial buildings lab, and also a industrial lab. We've got roughly 250 folks, mostly of which are researchers and scientists, and about 60 or 70 of those are in the end-use group, of which I am a member. Quick PAR overview. We are another Midwest Building America team, proud to be working with the NorthernSTAR team and coordinating with BSC on these projects. We do most of our work here in the Chicago area, but also partner and have some projects in surrounding states, working in Ohio, Iowa, and then a few targeted collaboration projects in some of the other states. We focus on space heating, water heating technologies, and cold climate solutions at large for high potential building stock. So for example, you can see a picture below of a line of single-family bungalows here in Chicago. Very typical. 40% of the single-family home building stock here in the city are bungalows, and so you can imagine that developing solutions for those types of homes can have pay significant dividends. As far as emerging technologies are concerned, this is sort of taking the research and development that we talked about earlier today and moving the successful technologies into the marketplace. And so beyond technical challenges, we look at market challenges, we look at programmatic issues. So can this be part of an energy efficiency program? How will that work? What kind of incentive do you need to offer? Who needs to get the incentive? Those sorts of issues. So I think that one thing that we learned here is that I think we're kind of working in parallel, where there's still the need for some field and laboratory testing as it relates to combi systems. But there's also, I think, a few technologies out there today that are ready for prime time, and systems can certainly be improved over time, but that we're ready to get these things out into the field in a more significant way. And I'll talk a little bit about that moving forward. Regarding kind of critical activities as it relates to emerging technology programs, in the case of integrated systems, look at characterizing energy use, cost effectiveness as it pertains to the homeowner, but also the utility and the total resource cost or other cost effectiveness metric used by a utility energy efficiency program, identifying market opportunities and also market barriers, and then developing solutions to address those. A lot of what we do is large-scale demonstrations. It's a good way to build awareness, build market channels. You heard Ben talk about the contractor issues. We think in this scenario, contractors are going to be a key component to the success or lack thereof for energy efficiency programs implementing integrated systems. The contractor is not only ultimately responsible for the successful installation and operation of the system, they have a lot of impact on cost effectiveness, and they also have the principal responsibility of selling the consumer on the technology. And then I think that the important thing through these demonstrations is to identify the unknowns, develop program data. So I think that through Building America, we can gather a lot of the technical information, and then we can partner on emerging technology programs such as this to fill out that information with market and program data. Activities typically include training, education, and outreach. So contractor training would be one, education for homeowners, and then general outreach and awareness. And then, like I said, developing solutions for the key stakeholders. So getting into the technology a little bit, we're focused on two key technologies and manufacturers. They're both tankless, water heater driven, condensing tankless, 90+ efficiency, upwards of 95%, combined with a hydronic air handler, so similar to the setup that you saw discussed earlier today. As discussed, this technology has been around for a long time, but what's new is that there are several manufacturers, two principally, that have for-purpose, fully integrated, pre-engineered systems. And so that's important for a lot of reasons. There's been issues with in the past with operability as it relates to integrating the appliances, domestic hot water prioritization, which has largely been addressed, and then installation issues. For an energy efficiency program, it's really important to get repeatable results and feel good that a large range of contractors can successfully install this equipment in a manner where they can get repeatable energy savings and also the operability and benefits that their customers expect. Right now, like I said, there are two systems on the marketplace. Rheem and Rinnai offer these integrated systems. There are other systems that are out there, but they're not fully integrated and supported by a single manufacturer. If someone has information to the contrary, happy to field that at the end. But additionally, these new systems offer better capacity for larger homes. I'm not sure if it's been discussed too much or discussed at length today, but one way you increase capacity of these systems is increasing the supply temperature of the water heater. And so instead of being at 120, it might be at 140 or 160 or even higher. What that can do is increase the potential heating load you can address through the system, but also can decrease the performance as it relates to the condensing in the tankless unit. And so that's something that we'll look at when we do some large-scale demos here. Sort of from energy efficiency programs perspective, why do we care about integrated systems? Well, here's kind of two reasons. One, I'm sure some or most of you are familiar with proposed rulemaking looking at regional furnace standards. So we'd have a federal standard that would raise the AFUE for furnaces, gas furnaces, to 90% from 80. And so what that would do is eliminate the possibility of 90% furnaces being a part of energy efficiency programs and decrease the value and energy savings potential from higher efficiency units that would be a part of those programs because your baseline would go up. Further exacerbating this issue for programs is these furnaces are gaining pretty good foothold in the market today. As As you can see on the lower right-hand corner, 2009 national furnace shipments are at 50% condensing versus non-condensing. This is higher in some markets, Chicago and Minneapolis included, I believe. So you've got market transformation taking hold, and so the attribution of the programs really moving people to buy condensing is coming into question. Further, on the hot water side, you have challenging economics for almost all high-efficiency hot water residential programs. The base level storage gas water heater is the savings you can achieve in moving from that to a high-efficiency system like a tankless, or a condensing tank. The nominal efficiency improvement is significant, but the overall therm and gas savings isn't huge as compared to the incremental cost. And so the payback for the consumer is challenging, and further the payback as it relates to the TRC, the regulatory utility cost-effectiveness test, is challenging. So what we can do through these integrated systems is fill a hole here moving forward in residential programs, targeting residential space heating, which is by far the largest program area for residential for many gas utilities, especially in the northern climates, and piggyback on that space heating load to find gas savings in water heating, where typically it was more challenging, but here you're able to use one piece of equipment for two end-use loads. So moving into kind of the customer perspective of all this, I think that having these integrated systems, you've got these large manufacturers supporting them, warranting them, training contractors. These are all good things as it relates to transforming the market, to getting these things into the marketplace. We think that there's a significant opportunity, given the relationships that these manufacturers have with plumbers across the country, with HVAC contractors. Like I said, you've got improved payback as it relates to investing in one piece of high-efficiency equipment, and the security, knowing that these manufacturers have a track record and will be around when and if there is a warranty issue. We've got an example comparison here, looking at the cost between mid-efficiency equipment on the bottom and high-efficiency tankless and an air handler unit on the top. These are costs from a participating manufacturer, and this is just equipment, not labor. But as you can see by this example, the costs are very near each other, and the tankless unit obviously offers improved cost savings and performance. And so they're targeting a big market in pretty much all forced air systems. There's a lot of flexibility. There's a lot of benefits as it relates to energy savings and otherwise. And so we think this is a place in energy efficiency programs, but there's still some work to do as it relates to breaking down those market barriers and moving them into the market. So that's all I've got for you, and I think we'll pass it back to Pat to field some questions. Thank you.
All right, now it's back here. Thank you, Armin. Thank you, Ryan. Two excellent pieces of the rest of this puzzle, if you will, on looking at this particular technology and where we might go forward. There are a couple of questions coming in, so we'll go to those. I think, Ryan, you hit it fairly well here at the end, but what's it really going to take for utility and other programs? Kind of what are the barriers, if you will, or what is it going to take to put these systems in the marketplace side by side with the more conventional equipment?
Yeah, I think that's a good question. And yeah, I think I highlighted some of those things, and maybe I'll reiterate it here. I think having major manufacturers with a presence in the marketplace is really important. Have customers having that comfort, getting contractors comfortable with it, having pre-engineered systems that rely very little on field engineering and make things simple for the contractor to understand. As far as integrating them into programs, we need more field data to help utilities feel better about the expected energy savings and cost effectiveness, and then tried and true program delivery mechanisms that can help them feel good that if they do put a rebate behind it, here's what you can expect, and kind of here's the way to go about it. But I think if we can bring the cost comparable to a condensing unit with a storage water heater, a typical storage water heater, and then throw a good incentive behind it, that would be really, really useful. I think one remaining barrier is what's the specification that would earn a rebate from a utility. I don't think we know if we have a good rating for the space heating the space heating efficiency of these systems. We have an energy factor for the space heating, or rather for the water heating equipment, but not necessarily for the space heating component. And so I think that's a question that we can answer through some of these Building America field tests.
Yeah, I guess they'll probably throw a little bit of a curveball here at both Armin and Ryan, but if the two of you would want to comment at all in terms of, we have focused a lot on this technology relative to air handlers or air distribution systems. Given your history and background, experience or thoughts about where this, is there as big of opportunity and or not, or where will this plug in, this same concept plug into hydronic distribution, such as radiators, baseboards, in-floor heat, that type of thing?
Sure, this is Armin. This problem is one that's, I think, been discussed in other venues, but just sort of to repeat, whenever you have a return water temperature that's certainly going to be above 120, 130 degrees, you have a problem with using a high-efficiency water heater that's intended to be a condensing water heater. So that pretty much throws out most baseboard radiators or large-type wall radiators. So I think that the real key here is to find systems that are going to use a much lower temperature for heating, which would be floor radiant heating would be ideal. It hasn't had a large uptake in the market, but there you're supplying maybe water at 85 to 90 degrees, which is ideal for being able to come back at a condensing temperature. We really push the limits with trying to get reasonable supply air temperatures with these hydronic systems and still get return water temperatures below the level that Ben Schoenberger was asking for, which is at 105. It's almost impossible because to try to get 105 degree supply air temperature and then have that as your return air temperature, it's very unlikely unless you use a very large coil, hydronic coil, and then your costs are going to be driven way up. So that's kind of my summary, that the two real applications are for hydronic or something cooler in terms of supply air or supply temperatures, and that would be floor radiant heat.
Excellent. Ryan, any thoughts on your end?
No, I'll punt to Armin or the other analysts on that one.
All right. Well, Ben, did you, Ben or Jake, want to respond? I mean, I think Armin hit it right on the nose there in terms of, the kind of this trying to hit this sweet spot of temperature, and maybe want to share just some of the experience we've had with the going to a different type of coil setup to try to achieve that.
Yeah, this is Jake.
Can you speak up just slightly, Jake?
Yeah, sorry, this is Jake. Yeah, Armin's got it right. I mean, that's where the work has to be done on these, and yeah, it's that being able to separate that supply air temp and get that up while you're still able to get that return water temp down. And we've played around with many different air handlers and found very similar performance across the ones that are designed to work with mid-efficiency units. The counterflow isn't sufficient to get that separation. We've worked with a couple other air handlers where we are getting it, and we're seeing just great results where we're getting air temperatures that are exceeding 150 and water temperatures. I'm sorry, the air temperature is exceeding 115, but the return water temperature is dropping below 100. So it's out there. It's not common though, and yes, the expense is there's a premium for it, but moving that piece into this, I think really advances the whole thing quickly because our efficiency jumps up, our comfort jumps up, and it's very comparable when you're retrofitting it with an existing gas furnace as far as the temperatures go. So it's that's kind of the crux of it right there.
All right, excellent. While I have that group on the line, we're going to bounce back to a question that's really more directed at the weatherization application specifically, and seems to be the real core of what we're presenting here, and that is, so what are the chances that this technology, as it's being tested by SRC and CE in a weatherization context, what are the chances that it might be approved as an approved measure or an appropriate measure for weatherization programs elsewhere?
That's a great question that we are hoping is a positive answer. It's really hard to predict at this point. So much of our funding is being cut. So even surviving as a program is on the line. Our goals from the beginning were to make sure that we could drive the costs down enough to make the savings to investment ratio work for this program. We have kind of an idea of what that cost range, the installed cost range should be, but again, that's run against each house. So we're confident that we can kind of get it in that range. However, as our funding gets cut, replacing both a furnace and a water heater in each house or in the houses that need it might become harder and harder. So we're working on it, but it's kind of based on a lot of politics, unfortunately.
All right. I think we're going to stay in kind of that retrofit mode for one more question, and of course it would be open to all of the presenters here, but just comments in general on this technology as a retrofit technology as opposed to buying all new. Just the physical aspect of moving a new air handler underneath the existing ductwork, et cetera, what kind of airflow rates need to be maintained, et cetera, et cetera. So I mean, just kind of, I think there was some comment about that earlier. We're going to kind of slide it under a duct system that may be good, bad, or ugly, and had been, fired by another different kind of piece of equipment. Other thoughts or things that have been learned in kind of how to slide it into an existing system. Let's start with maybe the SRC CE group, and then we could move to Armin or Ryan.
Yeah, this is Jake. That's a challenge. When we're going in and doing initial site visits in houses to see if they're going to work for this type of retrofit, amongst many other things that we're looking at is where the central air, where the A coil and the drip fan are located, and what's the distance from the ground up to that. So we're mindful of that, and there's a wide variety of air handlers that have varying heights. So we're trying to be able to keep our install costs as low as possible by not having to touch or move any part of the AC system if it exists. I am noticing that on a decent number of homes, there is some need to redo the return drop that exists. I don't know if that's just our housing stock, but there's some pretty easy ways to increase flow with just a little bit of sheet metal work there. So again, it's the constraints that we're placed under. We'd love to be able to do more and be able to get better flow, lower static pressures on those systems, but we kind of have to work with what we're given. So, all
right, I'm going to do a follow-up question here for Jake, and then we'll pop back to Ryan and Armin if they have their comments. But the fact that you're going for this lower temperature, potentially you're pushing a higher airflow through the system perhaps than you had with the previous inefficient furnace. How does that intersect with duct leakage and other issues on that existing system where you're basically trying to push a bit more air through the system than perhaps was in the past?
Yeah, that's a good point. I mean, if we are in a situation where we're increasing the flow, we're going to exacerbate any issues with imbalance in the supply and return ductwork. And what we're noticing is when we have to take an air handler that was designed to work with a mid-efficiency heating plant, those are the systems where again, as Armin had mentioned, it's hard to get that separation. So your resort is, well, I can play with the flow rates, I can play with the airflow rates and the water flow rates and the set temps and try to make this work. And when we get these air handlers that are designed with a better coil, they're actually doing that better performance at a lower CFM rate. And so it's a great when you can get into that middle spot and get the performance that you're looking for. Oftentimes you're getting that with a lower fan flow rate. So it's kind of counterintuitive, but it really depends on what type of air handler and how you're integrating it. So.
Excellent. Armin or Ryan, any comments to kind of some of the kind of the physical issues of planting this new technology under an existing duct system or into an existing hole, if you will, or footprint?
This is Ryan. I just have one quick comment. I know that the manufacturers we're working with have targeted the retrofit market and have built their air handler units on the same chassis and to be the same size as their existing furnaces. And so they expect this to be plug and play and kind of have the same benefits and potential drawbacks of replacing a furnace with a furnace. And so it should be able to integrate with any coil. It should fit on in the same space. And then as it relates to the water heater, there's a fair amount of flexibility. You've got a smaller, if you're going tankless, it's a smaller setup, and then you've got you can pipe over to the air handler unit. So I know that they want to be able to install these things for a reasonable cost in as many circumstances as possible, and it seems that they've been fairly successful in doing that. But that's what I've heard.
All right. Additional thoughts, Armin, or?
Yeah, I agree with on the air side, the more or less one-to-one substitution for size from a furnace to a hydronic air handler. There's always probably going to be some sheet metal work that needs to be done, but that's sort of inconsequential, and it would be the same for both. One of the things that I've noticed is that usually these change-outs are happening in conjunction with other improvements, weatherization improvements, which is actually bringing the load down. So usually the duct system is not going to be too small unless it was much too small for the first system that was serving that space. So I think that goes in the right direction, i.e. the load is coming down, so the airflow requirement could go down, but you're using the same size duct. With regard to the gas side, the tankless hot water heaters, for instance, are smaller, and that's very nice. They're compact. But the biggest problem is that they often require a change-out in the size of the gas service. And going from 1/2 inch to 3/4, or if there's gas fireplace and spa or whatever, and maybe that's not a weatherization house, but you might even have to go bigger than 3/4. So that is certainly a concern, is potentially having to change the gas service.
Excellent point. Yeah, we had a note here from Greg referring to the work in Utica, in the deep retrofit work. They said found it best to seal a ductwork to leak not more than 3% of air handler flow at the 25 Pascal test pressure, duct test pressure. So clearly they're trying to address the duct leakage at the same time as the change out. I'm going to back up here to a question, kind of a broad question in terms of really the whole technology. How do we address the lack of accurate ratings for these boilers and combi systems? And in some cases, they may or may not be reflecting properly idle losses or other efficiency issues at a wide range of load conditions. I mean, it's like I said earlier, it's not apples and apples anymore. It's a different system, and do we need a different way of talking about efficiency or measuring it or communicating that to the user, whether it be the HVAC contractor or the consumer. Maybe Ryan, do you want to start with that one?
I don't have, I think there's probably other folks on the phone who can give a better technical answer, but I know that from a, a program's perspective, that's certainly an issue because I think the kind of working assumption is, just use the energy factor of the water heater, and that'll be a good proxy for the space heating efficiency. And I think that we know that there are variables at play that can influence that to be close to the truth or to be, maybe not so close. And so it seems like that's something that does need to be addressed as we move forward.
Yeah, maybe one of the issues in that question was these idle losses, which Ben hit on in his early slide in his presentation. Clearly, there are some standby losses. There are pumping losses or pumping energy involved here. Any comments or thoughts about that and what we need to have maybe a better, cleaner message for folks moving forward as to kind of system efficiency?
I guess I would say this has been, I would say ASHRAE is currently doing some work to try to update their method for rating combi or dual integrated systems, and I think some other groups are looking at that as well. This is a kind of common problem for a lot of mechanical equipment. I know the energy factor is, some work we've done here and others have definitely done have shown how that doesn't necessarily reflect well or compare well between technologies. So I think all of the, these sorts of questions apply to a lot of these rating methods. One big factor is something Ryan mentioned earlier is that it's really hard to rate these systems as a whole for performance if they're not all from the same manufacturer. Or, you kind of have to piece them together because it's hard to give a heating plant a rate, a water heater a rating to be used in a dual integrated system without an air handler, because it's going to be different depending on the coil size and different things like that. So there's a lot of variables to be accounted for. One of the things that we need to know is, we need to have a little more field research, and hopefully we'll be able to supply some of that just to get an idea of what these installed efficiencies are. But people are working on that question, so hopefully we'll have something sooner rather than later.
All righty. Any other thoughts, Armin, or anyone else on that?
Yeah, this is Armin. The ASHRAE Standard 124 from 2007, Combined Appliance Annual Efficiency, is one of those standards that is trying to be updated. They're working on that. And also the Canadian Standards Association CSA P9 of 2011 is in process. So there's no question that the standards and the methods for evaluating these pieces of equipment and their efficiency is something that needs to be improved and is in process. And you easily could get systems that are not performing as you would expect because these standards as they currently are do not always reflect the right kinds of conditions, loads, and draw rates, et cetera, and temperatures that you may have that need to be considered.
Excellent. Well, I think that's all the questions we have for right now. I think we covered a lot of ground today. I really want to thank our 5 presenters and Chuck as well for joining us. I think it went really smooth. I appreciate all your help on this and sharing your insights on this particular technology. I thank all of our attendees for joining us. I hope you get